record, and then I will absolutely post this as we get done. And then after we get done with this, anybody has any questions at the end, they feel free to hang out, and I'll be glad to discuss anything. All right, so let's go ahead and get started. This is chapter 11, okay, our 13th week, 13th lecture. And this titled Images from Space. It's going to be dealing with satellite remote sensing, satellite orbits, sensor resolutions, those kind of things. And then we'll talk about some of the different types of satellites that are being used. Some of that might be a little bit dated. This is an older book, so there has been developments, and some of these have changed because of just, you know, the time interval since this book was written and what's going on now. So they are pushing this constantly. As you guys know, how things change pretty rapidly, especially in this kind of thing. So we're going to look at how the remote sensing type satellites collect data. I mean, we talked a little bit about the remote sensing process, you know, looking at the bands and those kind of things last week, kind of build a little bit more on that. But more specifically, it's going to be dealing with the satellites themselves. And then we want to look at the capabilities of satellite sensors. So, you know, there's a lot of ideas about, you know, people have, you know, how much data you can get from sensors, and some of that's science fiction, and some of it's probably reality that we don't even know yet, because I'm sure that the government, you know, the federal government and the aspects probably know a little bit more than they let on. We're going to talk a bit about Landsat. Landsat is the American system of remote sensing satellites that have been in effect for quite a while. And you know, you can get images that go back to the 70s, and so we have a continuous stream of data that's available to us, which is kind of cool. And then we're going to look at satellites that have high resolution sensors. These are the ones that are really starting to push the limit. And now most of these are probably not government related type satellites. These are probably private venture type things. So the data that they collect is the stuff that would probably be being sold actively to people. Now, most of the government, the federal stuff, a lot of that's free or at minimal cost, at least. So there's a difference, but there's also a difference in resolutions and what you can do with the data. And then the last thing I think we'll talk about is using satellites for monitoring, which I think that, you know, everybody probably understands that concept. But that's what we'll look at. And in chapter 12, if you have time to read it, it deals with environmental modeling. Some of the stuff they're doing with it's more specifically. I kind of skipped that chapter because it really probably doesn't pertain to us as much as some of these other things. So that's what we'll get into. Okay, so let's take a look, introduction, kind of look at, you know, you hear a lot of things about this, and most of this is based on fictional stories, but if you listen to that, you get the impression that remote sensing and satellites in particular can basically observe anything on Earth. And of course, that's absolutely not true. We probably know that, but for instance, you know, you may heard that you can rotate them instantaneously into any required orbit, and that's not possible or feasible at this time frame. Being able to track people, a specific person, perhaps, again, that's probably science fiction by and large. Being able to do things like read a license plate off of a car. Well, that stuff is starting to happen actually if you get your sensors pushed down to the limitation of what you can read. But again, they're probably not there yet, but the resolutions are increasing, and they're increasing pretty drastically. So at some point we may be able to do that kind of stuff, but I think currently not. And to do things like read lips from space, I'm sure that's pure fiction. But again, some of this stuff is changing widely, and as we get better with our sensors, that stuff was going to really maybe become reality. Because just think about things that 20 years ago we thought really wouldn't happen, and how they're used now. So satellite remote sensing will be examined to determine what the real reality. The reality is what we're really using, and then the limitations. So that's what we're going to kind of look at in this chapter and what we're getting into. So let's start out kind of at the beginning and look at the primary images from space that you would talk about. The first true man-made satellite that achieved any kind of orbit was Sputnik, and that was launched in 1957 by the USSR, and that created quite a commotion, particularly in the U.S., because at that point we were starting to get into the Cold War, or actually were in the Cold War, and when the Russians launched Sputnik, and they had that ability to show that they could put a satellite up there in orbit, and it actually broadcast a signal that could be picked up. That had real wide implications in it, and it really kind of galvanized the U.S. because we were not there at that point. Interestingly enough, if you guys have been watching the news, the Russians have just also come up with a. They say that they have a virus thing for the coronavirus, and it's named Sputnik too. So that's kind of an interesting thing on that. But the U.S. Followed quickly with the launch of their own satellite. It was called Explorer 1 the following year. So by 1958, we had caught up with them, not superseded them. But like I said, because we weren't the first, it was kind of a bad thing for us, as our nation. And this established the ability for satellites to be able to have uses. So one of the things they were able to do then was carry equipment. And some of the things they began to experiment with was things like scientific equipment. So you could do measurements of certain types of things, particularly probably things that were pertaining to Earth's atmosphere, those kind of aspects. Then they, again, began to look at remote sensing equipment. So having that as payload on there, whether that was photogrammetry or photography types of equipment, or the other types of sensors that we would talk about. Now, LiDAR wasn't available at that point, so we didn't have those kind of things. And then other types of payloads that they began to use. So all of this developed pretty quickly. And after all of this happened, NASA was developed, the National Aeronautics and Space Administration. That was established to head up the space program in the aeronautics aspect, and that was established in 1958. So that came online right after and about all of this. And again, maybe if Sputnik hadn't happened, that wouldn't have spurred us on quite as quickly. But once it did, it came on in a tidal wave of force. So remote sensing, reconnaissance, and surveillance began in the U.S. with a program called the Corona program. So again, remember, this was Cold War aspects. This was when we were starting to get into that pretty heavily. And of course, a lot of that was probably with Russia and the USSR at that time. And I'm sure they were doing the same thing with us, and still are, But this program was in operation from 1960 to 1972. So it took them, a couple of years. If you look at that, NASA was established in 1958. And by the 60s, we had this pretty robust program that was in effect, and that lasted for a good long time. In fact, it superseded the Cold War itself. Corona satellites were kind of different because they employed an onboard camera, actually. So they were using film, and at that time, of course, digital film wasn't a thing. So this was using real film. So this took pictures of selected ground area. And of course, it would probably have been sensitive areas of different parts of the world. And this film, after it was developed or exposed, it would be ejected, and it was retrieved by U.S. planes. So if you think about that, that's a pretty complex way of doing things, to actually have to do that. And the film was developed, and it was used to provide intelligence information for areas around the world. So it had to be brought back to Earth, developed, and then it was given to people that did photo interpretation, the kind of things that we had talked about in the other couple of chapters. So during its time frame, it provided 800,000 images plus, and that's a lot of images if you think about it. And I don't know about all the logistics of this, but if they were using camera with film, you got to wonder how that actually worked. How they actually had enough film in there to be able to do that, or if it had to be somehow redeployed with that. I'm not sure. But this program ceased operation in 1972 because at that time we had other types of satellite surveillance. I'm sure that came in. And those images have since been declassified. So since 1995, you would basically have access to them. Any civil person could actually probably get a hold of these these images if they really wanted them. This is an example from 1966, a picture from the Corona imagery. This is an Air Force base in the former USSR. And what it's showing you is bombers and transports and those kind of things. So I'm sure we were actively doing this, and you got to believe other parts of the world were actually doing this as well. So there's a lot of advantages when you look at this to using satellite remote sensing. And we talked about some of the things when we talked about the photogrammetry section, but one of the things is that a satellite will constantly orbit the Earth, so it can take pictures, you know, continuously. And also it can get the whole world. And of course, you don't have to worry about having some person interaction with it, so it's just up there. The one thing that's good about them is there's no need to fly over a hostile area or fly a plane particularly, because if you remember when we talked about the spy missions that occurred back in the photogrammetry section, you know, we had the U-2 spy planes that were up there, and one of those actually got shut down, and the pilot was discovered in Russia, and that became a big international kind of thing. So we didn't have to worry about that anymore. That was moot. And satellite imagery can image a much larger area. So a plane's going to be a little bit more focused because they're flying, for one thing, at a lower altitude, where a satellite's way up there. So you're going to get a bigger swath of area that you're getting. Now, of course, there's a trade-off for that. Your resolution is probably not as good unless your sensors are good. But it does provide global coverage, and of course, it's going to be much lower cost. So there's a severe amount of advantages when you look at that. And of course, this is not going to be restricted to geographic boundaries, because technically, if you're up there in space, you're not limited by any one nation's boundaries. So you basically can, you know, that satellite goes wherever it can see, essentially. All right, so how do these satellites collect data? So let's look at that. Not specifically the sensor itself. We'll talk a little bit about that, but we'll look at other things. So your remote sensing satellites, they have a orbital kind of plane or path around the Earth that they follow. And really, GPS kind of uses this exact concept. They use the orbital planes, and they have a certain way they orbit, and these guys do exactly the same thing. But there's different types of orbits. So what they have is one type called a geostationary orbit, in which stationary means, of course, it's set, or it stays put. So in this orbit, it's basically orbiting around the Earth at the same speed as the Earth. So basically, from the standpoint of where it is, it's stationary. It's not moving. So what that has is the ability to monitor the same place at the same time of day always. Okay, so it's just getting continuous read on one section. So that's what we call geostationary orbit. What they call a near polar orbit, which is a lot of what the surveillance type satellites or imaging satellites use. This is an orbital path that carries the object around the Earth, and it passes over the North and the South poles. And some of the GPS do that, but they're also on other orbital planes, so they're not all just strictly near polar. But a lot of these satellite surveillance ones are going to be this type of orbital plane. And this makes slightly more than 14 orbits per day in a 99-minute orbit period. So this is a good example of what we're talking about in that near polar orbit. And you can see the red sequence of arrows. That would be the actual satellite itself. And what you're seeing, the dotted line, that is your ground track. So that's what it's seeing. And the width of that is going to be fixed by the sensor. We'll talk about that a little bit. So it's not going to be like hugely broad. It's usually limited to so many miles. But also that as the Earth turns too, remember, you're getting different locations on that Earth. So it's just not one continuous band always at the same point. So during a continuous orbit of this type, your satellite's imaging the ground underneath it, and basically it's using a nadir type of thing. So in other words, it's looking straight down onto the ground. Now you can do not based on nadir. We'll talk about that in a minute, but usually you're looking straight down. So your image is limited to a certain size on the ground, and basically, of course, that's going to be a function of altitude and also the sensor itself. So those are the two things that would kick into that. And what you're getting is what's called a swath width, and this is the width of the ground that the satellite is actually seeing, or I guess I should say the sensor is actually seeing. So a typical Landsat satellite sensor has a swath width of 185 kilometers. So that's giving you a pretty good cross-section of ground as it comes across. Okay, so as it orbits, also remember that the Earth is rotating beneath it, so you kind of have two motions, the motion of the satellite following its orbital path and the motion of the Earth following its rotation. So several days are going to separate orbital paths and swath widths. In other words, you're not always going to be hitting the same swath width as you come around. It's always going to change a different location. And depending on the period of your orbit and the period of the rotation of the Earth, you're going to have a kind of a sequence of swath widths. We'll see that here in a minute. So in a certain amount of time, the satellite's going to completely pass over all areas of the Earth's surface, and it may take a while, but for a series of Landsat satellites, it takes those guys approximately 16 days to cover the Earth's surface. So what that's saying is you're not going to hit the same point on the Earth for 16 days. So if something is super time sensitive, you know, a 16-day time period in let's say a war or something could make a huge difference, okay? So you wouldn't necessarily want to use this type of satellite surveillance system for something that needed to be monitored regularly. That might be a case where you're using a geostationary type of satellite placed into position over the location where you need to get it, so it gets it constantly. So this is out of your book. This is a good picture showing you the concept of path swath widths and the continuous time frame. So notice you're coming across at the ground track on day one, and so that the color, that yellow color, represents the swath width, whether that's 185 kilometers or whatever. And then notice on day two, you're in a completely different location, and then it goes back to 3, it changes. So you notice how that's changing back and forth, and then ultimately you get to day 16, and then that repeats. So you'll be back here at day 1 again after the 16th day. So this is showing you what would be a typical Landsat type satellite. So other types of orbits that we have are what we call sun synchronous orbit. So in this case, your orbital path is set up so that your satellite crosses the same area at the same local time every day. So for instance, it might cross the equator at the same time every day. And what this does is your images will have similar sun lighting conditions based on that. So these are cool because they can be used to compare changes of areas over time. But you know, remember it's a 16-day time frame. So Landsat uses a series of satellites in sun synchronous, and it crosses the equator at a constant time every day. So that same satellite will cross the equator at the same time. But remember, because of the rotations of the Earth and the motion of the satellite, it's not hitting the exact same swath. So that takes the 16-day time frame. Okay, so onboard sensors have basically two types of methodologies that they use for scanning the ground, if you will. They have what's called the along track, and they have the across track scanning. So along track scanning is a method that's used by a linear array. It's kind of a fixed array, and it just moves with the direction of the satellite. So the satellite has its path, and as it moves along, it has a fixed kind of array of sensors on it. And this is referred to also as what they call a push broom sensor. So if you think of like a push broom that you would push forward, when you push that broom forward, that broom going forward would be the motion of the satellite itself, and the bristles on the broom would represent the little sensors. So they're fixed, and they're just actually gathering the data across them. Okay, so it's pushed in a straight line due to the satellite itself, and that represents, and the bristles represent the sensor. Okay, So each little bristle, think of that being part of the array that's sensing the ground. So you have that one fixed sensor with all those little pixels in there that'll gather the data. So that's what we call the along track method. And this is an example of the along track. So what you notice here in this picture, it's showing you the ground resolution down below. The big blue arrow is showing you the motion of the satellite, and notice the sensors above here, it's just gathering. They're at a fixed distance, and this thing is just scanning it as you go with the motion of the satellite. Okay, so that's what you call the along track, or what they also call very often, and that's called a push boom. Then you have the other type, which is a cross track. So a cross-track scanning method uses a rotating mirror, and so what happens, this thing sweeps back and forth. It'll sweep left and right, so you have two motions going on here. You have the satellite moving along its track, but perpendicular to that you have a sweeping motion, and so this is referred to as a whisk broom type of sensor. So the whisk is the motion left and right, and it's going it's going with the path of the satellite, so it's got the two motions that it develops. And you can think of, again, as the broom back and forth, that's across the path, perpendicular to the direction, and then each bristle in the broom represents an array within the sensor itself. So this is a pretty good picture of this. So again, the big blue arrow is showing you the direction that the satellite's moving in. And you've got this rotating mirror up here, so that's sweeping back and forth. So it just sweeps across, sweeps across, sweeps across. Okay. What it's actually doing, if you think about this, if you start at that corner right there and you go across, it's kind of like you're filling a row, and then it moves down to the next row, and then it goes to the next row. So basically, it's filling a column across, and then it goes to the next row. That's basically the way a raster would be set up. So that's why the upper left corner of rasters are always at 0, 0, or 1, 1, and then they move across to the right, and then the next row down will be 2, and then 3, and then 4, because it kind of correlates with exactly how a satellite is imaging it. Okay, so this is what we call the across-track scanner, or again, the whisk broom type of scanning technology. I'm not so sure the efficiency of one over the other, and I would have to think there's less mechanical parts going on in the long track scanning, so that probably from the standpoint is you don't have maintenance or any kind of thing that could break down in that satellite sensor. That's probably a little bit better than probably the across track, because you got that motion going on with it. But I'm not so sure if there's any difference in the resolutions or those kind of things, or which is better. So after your sensors have collected data, then that data has to be brought back down to Earth and then processed. So we said that the corona, the way they did it, they actually used photographs, they used the cameras, and then that film had to be retrieved by a plane and then brought down to Earth. Well, in this case, we're dealing with more digital data. So that information is going to be downloaded from your satellite, sent to Earth, and processed. And there's a collection point called EROS. And EROS is the Earth Observation Science Center, which is located in South Dakota, and it serves as your download station for your satellite imagery. And it's several, probably, I think not just one satellite. It probably processes other ones as well. Primarily federal, probably U.S. types, but there might be other ones that pay for that service. This is located near Sioux Falls, South Dakota. And it receives data from numerous satellites. And again, I'm not sure if they would all be US satellites. There might be other ones you might be able to pay for this to handle that. So the data can either be directly transmitted to Earth via the satellite itself, or it can go to a relay satellite, and that satellite again brings it down. So it just depends on how it's set up to do that. Okay, so when we look at the sensors themselves to determine what they can see, kind of thing, they are broken down into 4 characteristics that define their capabilities. And we talk about what's called spatial resolution, radiometric resolution, temporal resolution, and spectral resolution. And those 4 things go together to make up what you're really experiencing in terms of how good your picture is going to be from that satellite as we look at that. So we're going to take a look at each one separately, and then we'll kind of bring those together. So the first one is spatial resolution. Now, we've talked a lot about this. This is really, when you hear the term resolution or DPI or that kind of stuff, or pixels, that's basically what we're talking about, spatial resolution. So what this is this is the size of the ground that is represented by 1 pixel on that satellite image, okay, or 1 cell of data. And remember, the smaller the number, the higher the resolution. So if we look at this, this greatly is going to affect the detail that can be determined from that image, because if you have a 50 meter by 50 meter resolution, you're not seeing much, okay? But if you can push that down to a 1/2 meter by 1/2 meter, you're seeing much more detail. So a 1 meter resolution is way higher than a 30 meter resolution. And these sensors are fixed at 1 spatial resolution. So that's a physical characteristic of the sensor itself. It cannot be altered. You can't just zoom in and get better resolution, okay? It's just fixed at what it is when it's manufactured. So a 30 meter fix can't be adjusted to a 10 meter resolution, okay? They are what they are. So what they can do is use algorithms to actually mix 2 images that or more that are not at the same resolutions. So basically it stitches these 2 together using an algorithm that allows you to use the one with the other to sharpen an image. So that is a possibility. So what we're looking at here is resolutions, and you can definitely see the grid squares. This is the same picture, understand this, okay? And we're looking at different resolutions. So doesn't say what the resolutions are, but obviously this is a much, you can see the square itself. You can physically see that square, okay? As we go to this one, you notice the squares have gotten smaller. So notice what's happening to the image, the sharpness of this versus this. Okay, this has gotten quite a bit sharper. And then this is a much higher resolution. So the images here, this might be representing a 50 meter, maybe a 1 meter, and maybe a 1/2 meter. I mean, I'm just speculating, but you can see the difference here on how that affects that. So if we take 2 bands of different resolutions and we stitch those together or use those, then we can do what's called sharpening that image. So we can basically get to a picture. Let's go back to this. You could basically take something like maybe this resolution and this resolution and mix them to get something like that. So it's a possibility. So that process is what we call pan sharpening. And we've already talked about the term panchromatic, and pan just basically means all or everything. So when we talk about pan sharpening, what we're doing is we're fusing higher resolution panchromatic band data with lower resolution multispectral band data to improve your clarity. So remember, panchromatic is basically doing visible light waves. So pan sensors measure only 1 large band of wavelengths. It's typically visible or near infrared spectrum. And multispectral is getting all kinds of bandwidth, okay? So you're taking that, but it can be, multispectral can be the lower resolution. And if you fuse that with higher resolution panchromatic, then you can get this pan sharpening process going on. So the next thing we talk about is what we call radiometric resolution. And so this refers to a sensor's ability to define fine differences in energy bands of measurement. So the wider the range of measurements the wider the range of measurements, the finer that sensor's radiometric sensitivity is going to be. And a measure of that is usually in a sensor's bits of precision. So we're talking about bits of data, and that's usually measured in like 8-bit or 16-bit or something like that. So for instance, in an 8-bit radiometric resolution, what that's going to do is place your radiance values on a scale from 0 to 255, because the 8-bit refers to a digital value where you're taking literally 2 to the 8th. So that's how you get the 256 numbers. So it's going from 0 at the lowest radiance to 255 at the highest radiance. If you push that bit number up, you push more what's going on, okay? So literally you're just taking and calculating the number of levels. It's based on a power of something 2 to whatever power you're talking about. So you typically see like a 6-bit 2 to the 6 would give you 64 levels. So that's not going to give you as sharp values because we're only going from 0 to 63. If we push that to 8-bit, we're going from 0 to 255, so you get 256 levels of data. You go up to like 11-bit or 12-bit, and notice it really goes up. So as you get to a higher number bit values, you get better radiometric resolution, which gives you sharper imaging as well, and more data that it can gather. Now, of course, when you do any of this, as you push those resolutions up, there's also that diminishing returns kind of thing. You get more data that you're gathering, so you're getting larger amounts of data. And any of you guys that have taken hugely large files and dumped them in AutoCAD, you know you can just crash it and cripple it. So the same thing works with any amounts of large data. Depending on how you're using it and what you're using it with, you have to have the ability to handle it and retrieve it and also store it, because storage becomes an issue too. Okay, so the finer the radiometric resolution, the better it can discriminate smaller differences. So what we're saying when we say finer, what we're saying is this higher bit number, okay? So that's this level at 2 to the 11th is much finer than at 2 to the 6th. So what we're seeing here, this is the effect of the difference levels of radiometric resolution as they would be simulated on what we would call different bits. So what we're looking at here, if this was a 2-bit image, this would be pretty low resolution, okay, radiometric resolution. So this is a simulated 2-bit. This middle image is a simulated 4-bit image, and this is a simulated 8-bit. And you know here, you can notice here, you get pretty good detail here. So it goes from 2-bit, 4-bit to 8-bit. Okay, temporal resolution would be the third type of resolution that we're talking about, and temporal basically means time. So a sensor's capability here is determined how often it can view the same location on the ground. So a lot of that comes into play with the orbits and the time it takes to get around in that orbit. So that's got really not a lot to do with the sensor, just the fact of where that sensor is being pointed at a certain amount of time. So for instance, if you were talking about the Landsat, that has a 16-day temporal resolution, okay? So again, that's not, the other two things we were talking about, the spatial and radiometric, those were built into the sensor, but this has strictly to do with the collection time period, how often it's hitting that same point, okay? So as we said, Landsat's every 16 days, so Landsat has a temporal resolution of every 16 days, okay? Now, temporal resolution can be improved by using what's called off-nadir viewing. So instead of looking straight down, you could send the sensor so that it could look left or right and take images in areas that it's not underneath it to actually help improve that resolution, in other words, the amount of time. So if it took you, 3 days to get to a point, if you did a little off-nadir viewing, you might be able to get to that point quicker. So they can use that concept. Okay, so that gives you the ability to not just observe what's underneath the ground, nadir viewing. Okay, so it's used to image locations away from your orbital path or your orbital plane. And this could be used in a case where you were looking at, where you had maybe a conflict going on in a war type of thing. So you can't necessarily get the satellite over to that area, but by pushing the sensor to the left or to the right in an off-nadir viewing mode, you might be able to see and monitor that condition more quickly before you would get back over to the point where you needed to see it. Okay, so the last one we'll talk about is spectral resolution. So this refers to the bands and the wavelengths that are being measured by the sensor. So this directly is built into the sensor. So this is a physical characteristic of the sensor, like the spatial and the radiometric were, okay? So this refers to again, the bands and the wavelengths that sensor can measure. And sensors are going to have different capabilities based on the energy bands they're measuring. And they all are going to do it somewhat simultaneously, but for instance, you may have one that does blue, green, red, and near infrared. That's kind of the standard. But if you have higher spectral resolutions, they can examine a lot finer energy wavelengths and a lot more of them. Okay, so, or in other words, we can break that down into different bands, not just blue, green, red, but we can do different bands of red, different bands of green, this kind of thing, into a much smaller. You can also then maybe do smaller infrared wavelengths, okay, which maybe even go the other way. Some of them might be able to do UV. Okay, so we're going to look at a group of the satellites that were primarily created by the feds and still in operation and have been used quite widely. And then we're going to take a look at some of the ones that have been used commercially over time and show you some of the higher resolution ones that we've been talking about. So Landsat has been around quite a long time. It's probably the longest running satellite program in the US, particularly with remote sensing type projects. So it was conceived in the 60s, but it was first launched in 1972. So, you know, that was about the time the Corona system bugged out, remember? So they kind of they're probably birthed in the same time frame, but this was based on sensor technology and not film technology. So our first Landsat satellite, Landsat 1, was deployed in 1972. It's still operational today. It's got several generations of satellites employed. So what I mean by it's still operations, Landsat 1, I believe, has been retired, but the Landsat program is still involved. So that's not saying that Landsat 1 is still up there, or the satellite group that was originally employed. I think there's 8 now, but I think there's actually a couple more. So we might have some newer ones. In fact, this book only goes to Landsat 8. There might be a 9 now. I haven't looked it up, but you can go up to their webpage and you can get a lot of information on that if you want to look up a little bit more about this. So this shows you kind of the period of when each Landsat satellite group was in there, and we'll talk about a little bit of the differences. But notice Landsat 1 started in 72 and it ended somewhere maybe like about 78. And in between that, you also had Landsat 2 satellites that were launched and Landsat 3. So you can see they had not a real long life time frame, but around 82, we launched the Landsat 4 satellite group, and that had a pretty good lifetime. And then the 5 came in, and that one had a real good lifetime. Landsat 7 and 8, and some of these I think the 7 is actually still operational, some of them, and 8. Now, some of them had some failures on them too. I'm not sure why they didn't have a 6, but so the 5 satellites, the first 5 satellites that we deployed used a sensor called the MSS, the multispectral scanner is what that referred to. And Landsat 4 and 5 MSS was capable of measuring different wavelengths, resolutions. So you could get blue, green, and 2 bands of infrared. So Landsat 4 and 5 were capable of that. And they also had a 6-bit radiometric resolution. So 6-bit, remember, was not bad. If we can push that number up, then of course we get better radiometric resolution, which then gives you better resolution all the way around. It had a spatial resolution of 79 meters. So that's not high level, okay? If you think about that, 79 meters by 79 meters on the ground. That's not a lot of detailed information, okay, if you think about that. So Landsat was not set up for surveillance, and it wasn't set up for high resolution, okay? So, oops, I think I went backwards. Whoop. Yeah, okay, all right, so these system of satellites were also equipped with what was called the TM, the thematic mapper. The thematic mapper had a multispectral sensor that gave it 7 bands of simultaneous energy that it discovered, or collected. So you had the band 1 blue, the band 2 green, and you can see this is in micrometers. You have band 3 red. So that's basically our visible spectrum, because if you remember last week, the human eye basically sees from 0.4 to 0.7. So those are in the visible ranges right there. And then it had the band 4 was a near infrared. So that just outside of visible range. And then you had middle infrared, which we can't see any of the infrareds. And then you had thermal infrared. So this actually had 7 bands, and then it had a middle infrared as well. So that the preceding thematic mapper bands were selected because they were key to certain studies, and we've already talked about those like last week. One of the things we said was the vegetative index studies, the NIDV type of stuff, where you can determine that based on the amount of red light bands that are being shed from vegetation or absorbed and the amount of infrared. Okay, so that was pretty key to those kind of things. And particularly for the bands 3 and 4, they used the vegetation monitoring, so that NDVI type of stuff we were talking about last week, that was really important to that. So the Landsat program has been a real push in the development of that. Band 5 was used to examine water content of plants. And 7 was used to in basically separating various rock and minerals. So if you think about that, that's pretty cool, because you know, we're running out of certain minerals, and by doing this type of satellite surveillance, some of those precious metals and minerals, this might help look into certain areas of where you might be able to find them. And band 6 was enabling you to monitor heat energy. So these thematic bands also had improved radiometric and spatial resolutions over the MSS bands, so you were higher resolution at that point. So Landsat 7, which was dubbed the 7th generation mission, that was launched in 1999, and it doesn't contain the MSS or the thematic mapper sensors. It carried a new sensor called the ETM+. So that was your enhanced thematic mapper. So basically it had the same 7 bands that the thematic mapper sensor had. It had the same swath width, which would have been the 185 kilometers, and the spatial and radiometric resolutions were the same. But what it did do is it increased your band 6 spatial resolution to 60 meters. So we went from 79 meters to 60 meters, so that pushed that a little bit better. And it added a band 8 to the application, which was panchromatic, which again was basically visible light, and then had a resolution of 15 meter spatial resolution. So that was really pushing it down, considering, you know, you went from 79 meter spatial resolution down to 15. Now, the other bands were probably still at 79 meters, but when you got into band 6, they pushed that to 60, and with that new band 8, they pushed it to 15. So by the conjunction, using all of those together, remember, you can push the sharpness of images better than what you would have alone. And this is a good picture of the Landsat image showing you, I think this is actually a picture of Landsat 7. They've all changed look configurations quite a bit, but that's kind of what they would look like. Of course, you got that big solar array that runs it. And that's kind of neat, showing you the swath width down below, how that's working, coming across the east coast of the US down along Florida. Okay, so each scene that it measures in the Landsat is about 170 kilometers long by 183 kilometers wide. And so these are referred to as scenes. So each scene, basically you can think of it as a panel of information. So it's 183 kilometers, that would be from east to west, essentially, by 170 long, that would be north to south, okay? So they're not quite a rectangle. And each scene is considered a different image, so it's gonna take typically several images to cover a single state or a single location. But if we were looking at a state, for instance, like Ohio, it's gonna take several of these scenes to get the whole thing. So to access your proper imagery, you have to know which scene you're tied to on the ground with. So Landsat uses what's called a worldwide reference system, which would just be like any of the other reference systems we've talked about. It's just one that's generating their own. This is showing you a picture of a particular scene. This would be in China, Beijing. And you can see prominently Tiananmen Square and the Forbidden Center. So this would be in a Landsat image. So when we look at that worldwide reference system, basically it's just a global system of paths and rows. So it's just a grid system. And your paths are used to identify the area near a surface that's present in that scene, and the road defines where you are north or south in that. So to divide your globe into a series of paths, which are columns, and your rows, which are going north-south. So for instance, Columbus is going to be included in the scene path 19, row 32. It's kind of like a section, town, and range in the U.S. Public Land Survey system. Now, Columbus contains an area, well, that contains an area larger than Columbus. So if you get that, you're going to get more of it. But you may have to be able to then work with a subset of that image, because if you work with the whole image, that data is going to be huge. But so this is what that's showing you. So notice this would be path 18. And then as we go from left to right, so those are your columns. Here's your paths, okay, and those are your rows here. So that would be path, the upper northeast corner of Ohio would be path 18, row 31, and Columbus would occur in 19 and row 32. And actually, you know, notice it's approximately in the center of that, Franklin County, but you know, it's including a whole lot of other counties around it. Notice Cincinnati down here, Hamilton County, we would be kind of a little bit north of the center, but we would also be getting, you'd be getting Kentucky and Indiana information as well. We would be path 20, row 33. So if the area of interest straddles two Landsat scenes, what you may need to do is grab two images and then stitch them together and merge them together. So for instance, if you're looking at Mahoning County in Ohio, that's in path 18, row 31, and path 18, row 32. So those images would be merged and then clipped by a subset of county boundaries. So you might be able to do that, probably not in a GIS software all that friendly, but you would probably have to use some type of remote sensing software to do that. I'm not so sure. My multi-spec might allow you to do that kind of stuff, merge them and clip them, but it would probably take another type of satellite type of imagery software. And as I indicated last week, that stuff's pretty pricey. So it wouldn't be the average type of software. I don't know that GIS software would have that capability. But the idea here is that you would merge them together, you would stitch them together, and then you would clip that out. You could use this, if you use the county boundary, if you could identify that or delineate that somehow, you could use that like a cookie cutter and it would just punch that out. That's the data, the subset information that you would get. And then you would discard the rest of it or just use it someplace else. You wouldn't have it. Because remember, if you're using all of that data, it's going to be really, really huge. Okay, so there's a big trend to make Landsat imagery available to the public at greatly reduced cost. Some of it's free. If you go to the Ohio view here, you can get that from those guys. And then there's America view. I believe both of these these are both online types of things. The USGS, the US Geological Survey, they're going to maintain certain data. They have this GLOVIS utility that they distribute satellite imagery across the internet, and so they have all of the satellite imagery archived from Landsat 7 from Landsat 7 imagery. Okay, not all of it. There is available data sets from Landsat 1 through 5. Remember, there was no 6. So some of that, again, may be at cost, and it depends on who you go to, but I believe this is free if you go to the Ohio View stuff, so you can get that from those guys. So this is an example of the Global Visualization Viewer, that GLOVIS that we were talking about from the USGS, and it's kind of cool because you can go in and define what you want. So notice this swath is what this scene is what these this is showing you, and over here it shows you the path and the row. There's your path and your row. It's also showing you latitude and longitude values. So you kind of basically take what you want out of that, and then you could make that downloadable. Okay, so in 2003, Landsat, what they had called the scan line corrector, the SLC, it failed, causing missing scene data within images. So without that, the ETM H plus produced images that were basically only 75% of a scene. So obviously that was a problem. but you can use data from other older information, older Landsat scenes, and you can use algorithms to fill in gaps of the missing data. So that hasn't been a problem. And there's a lot of that Landsat 5 TM data that's still being used by researchers. So this stuff is actively being used, and a lot of, again, environmental monitoring and those kind of things. These guys use this quite extensively, because if you think about it, we've got data that goes back to the 70s. So from 70 to 2000, that's a good chunk of data that's available. Okay, so the most recent development, and I think, like I said, this one wasn't deployed. This one I think is still out there. So the latest generation of Landsat is Landsat 8. It was successfully launched in 2013, and its operation was transferred. I'm not sure who actually was running it. It might have been NASA before, but it's now been transferred to the USGS. If you click on the link there, you've got a link where you can get to that link. That'll give you information based on that, and you can get more information about Landsat in general. Okay, so Landsat data stretches back 30 years, and remember, that's a huge chunk of data. So that gives scientists the ability to monitor large areas of the Earth over time, and especially things where you're looking at different types of applications, things that are dealing with like long-term data trends. So we can look at things like growth in urban areas, and I think we've kind of seen this before. I think if you recall, we looked at pictures of Las Vegas that started in like the 70s, and then they go up into the 2000s. One of the big things that's very important is the patterns of deforestation that are going on everywhere, particularly in rainforest areas. And one of the things they have is a lot of data that demonstrates this, in particularly the Amazon basin, where those are areas that are important because they're high biodiversity areas. You can also do things like track movements of invasive species. We've had a lot of problems with invasive species in this country, for particularly things like, we don't have any ash trees, so to speak, of anymore in the east because of the emerald ash borer, and there's other critters that are coming in and other things. So you can do things like that by looking at that. Remember, we talked about spectral signatures. It would be possible to determine ash based on its spectral signature, or you've got other trees and whatnot that are under attack, things like oaks and those kind of things that are happening due to this kind of stuff. And then, of course, certainly monitoring aftermath and natural disasters. I mean, we are getting hit by a barrage of hurricanes this year, particularly down in the Caribbean area and those areas. So, I mean, you can imagine all of the satellite surveillance information that's going on with that. So this is a pretty interesting picture. This is showing you the deforestation that's happening. These are Landsat images of Brazil in an area, in a forested area. I'm not sure the time frame on these. I don't think it has dates on it, but what we're looking at is, this is the oldest image showing you an area in the rainforest. So this would be the second, third, and this would be more present time. So what you're looking at is how this deforestation pattern emerges, and it's kind of interesting because it starts out basically with a road that's cut through. So you have a road that comes down through here. So most of this would have been all intact rainforest at one time to the east and the west of that, of that road. Over time, what happens is, from the roadway, either logging or you have squatters that come in and they begin to cut past this way. So notice the deforestation is going in. Look at those complete vertical lines like that. So what's happening, you're seeing that concept going on. And then, of course, that starts to widen, so it bleeds out. And then ultimately you get to the point where it just becomes one big swath of development. Or what happens a lot of times in rainforests, when they are cut over, it's brought into agriculture. And the problem with rainforests is, once you cut them, the soils in rainforests are really, really horrible. So they basically just turn to concrete. And so rainforests just don't come back. Even farms, over time, the farming in these areas, it depletes the nutrients, and then the farmers move on. So a lot of it's what they call slash and burn. So these guys will come in here and slash and burn the area, and you'll get crops for like 2 or 3 years, and then the soils just become depleted and they move on. So that's a big problem. But it's interesting to see the pattern of how this develops. And you wouldn't be able to see that, but we've got 30 years of data or more of showing this kind of stuff. Okay, so NASA operates also remote sensing projects. They have capabilities that are related to Landsat. They have the EO1, Earth Observing 1 is what that stood for. Satellite was launched in 2000. It orbits 1 minute behind Landsat 7, so it just kind of follows up on it. It has multispectral sensors as well. They have one that's called the ALI. That's the Advanced Land Imager. It's going to be similar to that ETM-H+, that thematic mapper that the Landsat's using. Now, it has 10 bands that are at 37 kilometer swath width. Okay, so their swath width is way smaller than Landsat, and its resolution is 30 meters. So that's pushing it pretty high. And then the panchromatic is a 10 meter resolution. So both of these resolutions are better than the Landsat at the time. And they have what's called a hyperspectral sensor, and that will gather 200 bands of data at a 30 meter resolution. So that's a really high level data. Now it gets a lot better when you start to get into some of these. There's a lot of private companies that are involved in this process, and they are really pushing the spatial resolution capabilities. So one of the groups is SPOT. Now SPOT was originally started by the French, and I believe it was run by the French government. I think it has since been sold and is a private concern. Then we have Pleiades, which is a private company, Iconos, QuickBird, and there's Worldviews. So these guys in the GOI, these guys are mostly, I think, private now. And I think, again, I think SPOT actually started out as a government concern, but it has since moved over to private. So we look at the differences here. So SPOT, it was operated by the French Space Agency and the Spot Image Corporation. So they've been around a while. We have Spot 1, started in 86, and Spot 5 was launched in 2002. And I'm not sure what their newest ones are. I'm sure they're still around. These guys have a 26-day revisit cycle. So Landsat's is better by 10 days, and a 16-day instead of 26-day. But they notice the resolution. That's 2.5 meter resolution, so that's way higher than anything that Landsat had. Anything that we've looked at so far, this is way higher. So 2.5 meter resolution, you think about that, that's a pretty small chunk of ground. Okay, that's a high resolution. Carries 3 sensors. So you have a vegetation 2, 1 kilometer resolution. That's going to be used for broad level monitoring. So at a kilometer resolution, that's not very good resolution. But if you're doing just broad type environmental monitoring, I mean, it's probably good enough for what you need. Then they have the high resolution stereoscopic. That's a 10 meter resolution. And that's going to be used for digital terrain modeling creation. That's what DTM refers to. So in other words, by using that, you can determine or generate ground elevations, basically. Then you have the high resolution geometric. That's a pair of sensors, and they're at 20 meter infrared and 10 meter multispectral. And again, mixing those, you can probably get better resolution, or not better resolution, but just better pictures. So 10 meter isn't as good as that 2.5 meter. And then you have the 5 meter panchromatic 2, and then you have a 2.5 meter pan, what's called super mode. So Pleiades, so this is a truly, actually a company, and I think a lot of these companies are now, I think some of them have bought each other out, so I think some of these are run by the same companies, I believe, over time now. But Pleiades, they have a series of high resolution satellites. They had Pleiades 1A and Pleiades 1B, and these were launched, you can see the dates, in 2011 and 2012 respectively. They were sun synchronous orbit, just like Landsat. So again, that means that it would hit the same point of the Earth at the same time every time it was coming across. So you're getting those sun the sun is the same every time that it hits that spot. You get imagery products that you can buy. So this is stuff is for sale. 50 centimeter black and white. So that's really pretty incredible. 50 centimeter. Think about that resolution. 50 centimeter color and 2 meter multispectral. So these guys have really pretty high resolution. Now again, at 50 centimeter, not probably able to read a license plate, but you're getting pretty close to that kind of stuff when you can start pushing that kind of resolution. Okay, the Iconos, this was started by Space Imaging Inc. It's now GOI. So I think Iconos has both is both GOI and Iconos. And these guys had both multispectral and panchromatic sensors in them, 4-band multispectral sensor, 4 meter resolution. So again, that's really pretty high level stuff. Panchromatic sensor is 1 meter resolution. And these would be, by mixing these two, particularly in urban areas, you can get real crisp, detailed images. Here's an example of GOI, and this is out on Dubai, I believe, where they're building that series of islands. Those are all man-made islands that are, I think these are now all filled with houses. Last time I saw images of that, you can look at that on Google Earth. QuickBird was launched in 2001. Digital Globe, 2 very high resolution sensors, a 4-band multispectral, 2.5 meter, 4 meter resolution. That's pretty crazy. Panchromatic was, look at that, 0.61 meter resolution. Again, very crisp, detailed image resolution. Worldview 1, this was developed in 2007. Again, that Digital Globe company, which I think some of these guys have merged, they also own Iconos. So these have panchromatic sensors at extremely high resolution. They're a 0.5 meter resolution. Worldview 2, that was released in 2009. It had an 8-band multispectral with improved sensor resolution, extremely high. So that's 0.46 meter resolution. So we're looking at, these are probably state of the art. Now again, this is a little bit dated, so there's probably some that are even better. The multispectral was 8-band, and that was 1.84 meter resolution. Okay, so GOI, and again, that's that GOI company. That was in 2008. These are extremely high resolution panchromatic sensor, 0.41 meter resolution. So that's really pushing it down. That was at the time the highest spatial resolution commercially available. And again, I don't know, that's probably been superseded. I've got to believe it has been, but in 12 years since this was written. And multispectral sensors, 4-band resolution at 1.6 meter resolution. Okay, so all of this satellite imagery is going to be pretty much commercially available from a variety of companies. A lot of these companies will take that data and sometimes clip it down and whatever and then kind of resell it. So you can go to this company called Satellite Imaging Corporation and you can buy different levels of data. And they're just kind of more or less brokers, I think, that just take that data in and you know, they'll sell it to you. So for people that are doing particular types of work, wouldn't be civil engineers or surveyors for sure, but this stuff is available for other purposes. Okay, so that pretty much finishes this section. So what you should do is go ahead and read through this, and you can finish this off on your own, and we will continue with this. We're going to do a little lab that starts on page 402, where we're going to be dealing with some Landsat 8 imagery and kind of taking a look at that. And we're going to use that little multi-spec program again. And that's what we'll be looking at. So if anybody has any questions, I'll stick around. Otherwise, I'll go ahead and get this formatted and pushed out there. And I will plan on seeing everybody on Thursday, unless something drastically happens and we get the word that they're not going to have us there on Thursday. I'll let everybody know that. But I'm assuming that we're good to go still. So if anybody has any questions, I'll stick around. And otherwise, I will see you guys then on Thursday. Okay.
See you Thursday.
All
All right,
right.
thank you. See you.
Hopefully we will, right?
Yeah.
Yeah, hope so. Okay. All right, I'll stick around. If anybody has any questions, yeah, just let me know.
Good.
Hey, Cole, did you have a question? Cole, did you have a question?
Yeah, I did. Sorry, give me 1 second.
No problem.
My fan's on real quick.
Oh, no problem.
So, did you have a? I just wanted to ask you about that test just to make sure.
I'm finished. I've got to finish those up. So my big push is tomorrow to finish them up. Okay.
Tomorrow? Okay.
Yeah, I'm so swamped, Cole. I know you guys.
No, I get it.
You guys probably think I don't do anything, but my whole life, no, seriously, it's just grading papers or running back and forth to classes.
No, I believe you. Trust me, I believe you.
So I'm,
Okay,
go ahead.
I could even imagine, like, oh, it's got to be insane.
Well, it is, and it's changing constantly, you know, and then I just got this dumped on me today
Yeah.
that, you know, we may have to, I mean, the good news is we're almost at the end. So, you know, that's not the problem, but,
You got break and stuff. You can chill
yeah,
out for a little bit.
yeah. So, are you looking to, or is your idea that you might want to try to drop the class? Because I'm not sure.
That's so. It's kind of tough because I obviously just don't want that because that grade will really mess up my GPA and stuff, and I just don't want that.
Yeah, no, I understand that. When's the last, do you know what the last day is to drop? I'm not even sure.
Next Monday.
Okay. All right. So yeah, I should have an answer for you by Wednesday, and if you just want to say Thursday, I can just talk to you Thursday. How's that sound?
Thursday after class or something.
Yeah.
Yeah.
Does that work for you?
Yeah, that works.
And then we can kind of make the determination and see. I can probably give you a pretty good idea what you're looking at grade, you know.
I would just rather like at least know.
Yeah.
Like what my grade's gonna probably look like instead of just like dropping it without having any idea what's gonna.
I understand, and I first of all, I really hate to have you lose.
I know it stings.
All that time and the money that's involved in what you've done. So I hate to see any student do that. You know, you've come this far, but I understand exactly where you are, and I understand what you're talking about. So
I'm not gonna give up on that degree either. I was thinking about it. Do you know if they're offering it next semester?
actually, this route surveying
Yeah,
that's supposed to be offered next semester. Yeah. And
Okay. Okay, I'll probably end up. That's what I was also waiting. I haven't scheduled my classes yet, so I was just waiting to know about that, and then once I know everything about that, then I'll go through and do that.
Okay, well, tell you what, I'll plan on getting that together for you for Thursday, and we can sit down and take a look at that.
All right, that'd be awesome. I
And
appreciate
then, you know, we can kind of make a decision, and if you wanted to drop it, you know, then we could go that route. Okay.
Are you going to be teaching it next semester as well?
Yeah, it's the same exact format. You know, nothing should really change. So having been through it once, if you do go that route,
Oh,
it should be a lot simpler. You know what is entailed in it. It's got a lot of work. So
yeah, it is. But
I mean, you still have to do the work. But
yeah,
are you planning on taking other courses too next semester?
Yeah, I think so. What I talked to Carol, I think it was last semester. She went through every class that I should be taking every semester, which helped me out. I think she just has me switching over from surveying one semester and then construction management one semester, and it's like that's how she had it planned out.
Oh, okay.
Yeah.
You know what? Hold